So welcome to this lecture number 8 of solar photovoltaics course, principles, technologies and materials. So we will first do a bit of recap of last lecture and then move on to the contents of this lecture. So in the last lecture we learnt about energy band diagrams. Which are basically EK diagram. E is the energy and K is the wave vector. So these diagrams for a single electron, the curve is like this. So this is a parabolic curve because E is equal to h cross square K square divided by 2m. When you plot it for a lattice, the situation changes. For a lattice, you have to plot this energy on all the reciprocal lattice space points. So this is you can say capital K, which is the reciprocal lattice space points, and then you get a kind of many curves for different zones. So you have curves like these, and you can have curves like these, and then we have this curve, and so on and so forth. Now here what is important is that you so basically material, if these lines are curves are continuous across the space, and you can always jump from one state to another without having a discontinuity, then it's not a insulator or semiconductor. However, if you have a gap like what you see here across the K space, there is a gap, there are no energy states present within this state, then this represents what we call as a semiconductor or insulator with an energy gap Eg. And if this maxima and minima of conduction band and valence band, and this the band on top is called as conduction band, and the band at the bottom is called as valence band. And if the maxima and minima of valence and conduction band coincide with each other, then it is called as a direct band gap semiconductor. So maxima and minima, maxima of valence band and minima of conduction band, they coincide in K space. And if the maximas and second one is indirect band gap semiconductor, if these two don't, if maxima and minima don't coincide. Okay. So for example, direct band gap semiconductors like gallium arsenide is a direct band gap semiconductor, indirect band gap semiconductor is a material like silicon. You can read the details from other books such as solid state physics by Kittel. This is a very nice physics book. You can also read electronic and magnetic properties of materials. By R.E. Hummel. These are few good books which you can consider for building a background on these topics. We have not covered them in full detail, so as a result you need to get better exposure if you want to learn more about these things. So key thing is, if you have energy states which are continuous across the EK space, and you can always find an energy state at any given energy level, that means it's a conductor. But if you have a forbidden energy gap where you don't find an energy state, then it's a semiconductor or insulator depending upon the magnitude of Eg. Okay. So presence of Eg, presence of a forbidden gap will mean it's a semiconductor or insulator. Now having known this, now next thing we want to know is what is the in order to calculate the in order to work out the carrier concentration. So carrier concentration we require, first thing is density of states. So which means how many energy states are available per unit volume, let us say, and then what is the probability of occupation. The product of these two will give you what is the number of carriers, because suppose you have 100 energy states, okay, but probability of occupation is only 0.5, which means there are 50 carriers which are there, alright. So that is what we need to do. We need to find out first what is density of states and what is probability of occupation. So let us first look at what is density of states. So density of states in a semiconductor. So density of states is given as we write it as dE, which is proportional to e to the power half. Okay. However, for a semiconductor we can write it a little bit more precisely. So for semiconductor the band structure is like this. You have conduction band, you have valence band. So this is conduction band, this is valence band, and we have a forbidden energy gap. Okay. So if you plot just D as a function of E, it is basically a parabolic sort of behavior, basically, or a square root relationship. dE goes as E in this fashion, alright. Now when you plot it, now for a semiconductor you have a conduction band and you have a valence band, so you need to plot the density of states in both the bands. So density of states in conduction band is given as dCE is given as we write it as Mn star, or Me star rather, into square root of 2 Me star into E minus Ec. So this is Ec. So here it goes from Ec to infinity, and here it goes from Ev to minus infinity, or some negative energy. So basically Ec to negative energies and Ec to positive energies and Ev to negative energies basically. Okay. So this goes from the equation is Me star into square root of 2 Me star into E minus Ec divided by pi square and h cross cube, where h cross is nothing but h divided by 2 pi. H is the Planck's constant, and this is valid for energies E greater than or equal to Ec. So of course at Ec this will become equal to 0. So you have 0 density of states at Ec and higher density of states at higher energies. So the energy, so states increase in number as you go to higher energies, and then dVe is analog of it. So this is basically mh star into square root of mh star into Ev minus E divided by pi square into h cross cube. This is for energies E less than or equal to Ev. Okay. So if that is the case, then you can plot these. So if let us say this is E, okay, then if I make a y axis here, let us say this is the y axis, then in this direction it goes as this, and in this direction it goes as this. Okay. So these are, you can say this is dVe and this is dCe. So we have found the density of states. Now the next thing we want to find out is, so this comes from the quantum mechanical analysis and we haven't gone into details of that, but basically we want to find out. So basically you can say that dCe dE, what would that be? That would be number of conduction band states per cc, right, which are in the present in the range, present in the energy range. What is the energy range here? Energy range will be E and E plus dE within that energy range, right. Similarly you can say dVe would be into dE would be number of valence band states per cc present in interval E to E plus dE. Okay. So here we say that E is greater than EC, and here we say that E is less than EV. Alright. So basically these are, they are numbers, number of energy states per unit volume. So we can say that numbers per centimeter square per EV. Okay. So you can do energy distribution in that fashion. Now what we need to know next is what is the probability of occupation. This comes from what we call as Fermi-Dirac statistics. Okay. So basically here Fe, so we write a function here. So this basically the Fermi function, we can say this basically it's a function. Fermi function depicts how many of the energy states will be filled by an electron, or in the case of valence band we can call it as a hole. So what happens in semiconductors is basically when you have so this is conduction band, this is valence band, you have energy gap Eg, these are electrons which are present. So at 0k you will not have any electron in the valence band, all of them are filled up to here because they do not have energy to cross over, but as you increase the energy some of them will cross over and they go to conduction band and then leaving empty states behind, and these empty states behind are called as holes. So these are electrons and these are holes. Holes are also carriers because they provide states for conduction of electrons. So Fe, the probability with which an electron probability of occupation of energy state by an electron is given as 1 over 1 plus exponential of E minus Ef divided by kT, where Ef is a reference energy which is called as Fermi energy, and K is the Boltzmann constant, T is the temperature. So if you plot this now here, so this function as a function of temperature, if you plot it for example at 0k, when you plot Fe as a function of E at 0 Kelvin for temperatures for energy less than Ef, when E is less than Ef at 0 Kelvin, then this will be e to the power minus infinity. So this will be equal to 0. So probability of occupation will be 1. However, when E is greater than Ef, then this will be equal to e to the power infinity basically, right, and e to the power infinity is a very large number, which means it will become 0. So at energy is greater than Ef, so this is energy Ef. So at energy greater than Ef, the probability of occupation is 0. So this is 0. At energy less than Ef, the probability of occupation is 1. And for of course the function is sort of undefined at E is equal to Ef because it becomes E exponential 0 by. So you can say that every energy state up to Ef is filled when, so you can take this as sort of 1. So but the mean value will come at half. So this function is asymptotic around half. So however, so what this tells you is that at 0 Kelvin for E less than Ef, the Fe is equal to 1. For E greater than Ef, Fe is equal to 0, which means all the energy levels are filled up to Fermi level, and at 0 Kelvin, and above Ef all the energy levels are empty. And as you increase the temperature, this curve goes in this fashion. So as you increase the temperature, the curve becomes like this. So this is at T greater than 0 Kelvin. So basically what happens is that this curve on this side follows the relation Fe is equal to 1 minus, so basically you can say approximately equal to 1 minus e to the power E minus Ef divided by kT, and at these energy levels it follows Fe is approximately equal to e to power minus E minus Ef divided by kT. Okay. So now this number becomes negative, so the Fermi energy at these, so the probability at these energy levels reduces, and probability at these energy levels rises. So basically what it means is that the carriers in this range have left and they have gone here. Now this is what, so basically essentially you can say that this function and the function changes around half. Okay, the function changes around a value half. So if you increase the temperature further, this curve will go in this fashion. Okay, so its node is at half. Now if this is the case, then so at E is equal to Ef, you can say the Fe is half. So at E is equal to Ef, you can say Fe is equal to half. And then if another observation that you make is, when E is greater than equal to Fef plus 3 kT, then you can write exponential of E minus Ef divided by kT is much larger than 1, and Fe is generally given as exponential of minus of E minus Ef divided by kT, and for E less than or equal to Ef minus 3 kT, this exponential of E minus Ef divided by kT, this becomes less than 1. As a result, you can write Fe as 1 minus exponential of E minus Ef divided by kT, and this is what we have written there, right. So if you recall, that is what we have written here. This is the behavior. So this energy is, so at these temperatures are the temperature which depict the energy which is E less than Ef minus 3 kT. So this 3 kT is sort of a number beyond which you start having significant changes in the curve on the both sides, and you can approximate this function because this value becomes significantly higher as at these magnitudes. So now if you want to find out the carrier concentration, now the carrier concentration is, for a given semiconductor, we say that this is our conduction band, this is our valence band, the dE goes as this, so this is dE, okay. So this is Cb and this is Vb, okay. And our, for an intrinsic semiconductor, so this is for a pure semiconductor, pure or intrinsic semiconductor. For a pure or intrinsic semiconductor, the Fermi level lies right at the middle. So this is the position of Fermi energy. This is Fe, okay. So you can see that. So this is if you now plot the let us say this is the value of Fe and this is the value of this is E and this is dE in this direction. So y axis is energy, okay. This is Fe. So if I now plot Fe, this is 1 here. So the Fe will go as something like, at a finite temperature it will go in this fashion, right. So this value is approximately, this is 1 and this is 0 on the y axis, okay. So basically the this region and this region, they are equal in area, it is symmetric around this value, that is half. Now what is Ne? So if you want to now plot Ne, this is conduction band, this is valence band, this is Fermi energy. So Ne is now equal to Fe into dE. So when you plot these, you get these lobes which show you. So, this is energy and this is N or P. So, electron or hole concentration. So, this is basically the hole concentration and this is electron concentration, and in an intrinsic semiconductor N is equal to, you can say Ne or Nh, okay, instead of N and P. So, we can say Ne is equal to Nh because the Fermi function is symmetric around the Fermi energy, and Fermi energy lies right in the middle of the band gap. Okay. This changes when you make a P or N type semiconductor. So, we would do that when we come back again to this. So, now what we do is that we go to essentially, so we say that for an intrinsic semiconductor, Ne is equal to Nh, this is taken as Ni, okay, and E and Eg is equal to taken as the difference of Ec minus Ev, okay. So, you can take mod of this basically. So, if this is your conduction band edge, this is your valence band edge, this is valence band, this is conduction band, this is Ec, this is Ev, then whatever reference you take, the Eg is the difference between Ec and Ev. So, this is your band gap, and this is given as this Ne is equal to Nh. For intrinsic semiconductor, this Ne is given as Nc into exponential of. So, we can calculate using quantum mechanical calculation same density multiply density of states. Basically, you will calculate Ne E as a function of dE into Fe. So, this is what will give you the electron concentration. Similarly, you can calculate the whole concentration NPE as D. So, this is DCE, this is DVE into 1 minus Fe, because we are looking at the other side, that is 1 minus Fe. So, if you do that, then we get Ne is equal to Nc into exponential of minus Ec minus Ef divided by Kt, and we get Nh as Nv into exponential of minus of Ef minus Ev divided by Kt, where Nc is essentially effective density of states in the conduction band, and Nv is equal to effective density of states in valence band. And you can see this from this expression. If you look at this, Nc is equal to nothing but Ne divided by some exponential function. This is Ec minus Ef divided by Kt. So, basically this is the probability function, okay. You can take this upstairs, you can take this up, and it becomes exponential Ec minus Ef divided by Kt. So, this is the probability function 1 over exponential whatever, and this is nothing, and this becomes the concentration. So, essentially the concentration divided by probability function is nothing but the effective density of states. So, that is why this Nc is taken as effective density of states in conduction band, and Nv is taken as effective density of states in the valence band. Now, so we say that Ne is equal to Nh is equal to Ni. So, we can also say that Ni square is equal to Ne into Nh, which means it will be Nc into Nv into exponential of minus Ec minus Ef divided by Kt into exponential of minus of Ef minus Ev divided by Kt, and if you put them together, it becomes Nc Nv into exponential of, so this becomes exponential minus of Ec minus Ev divided by Kt, and Ec minus Ev is equal to Eg. So this becomes equal to Nc into Nv exponential of minus Eg divided by 2 kT. So Ni is Nc Nv to the power half exponential of 2 will not be here, now the 2 will come. Okay. So basically you can see that intrinsic carrier concentration is an exponential function of temperature and band gap. So as the band gap decreases, the Ni will increase for a given temperature, and as the temperature increases, the Ni will increase. So the lobes that you saw there, they will, so this is at, let us say, temperature T1. So this lobe will be, let us say, at temperature T1. If the temperature T2 is higher, then this will become bigger. So this will be at T2, but they will remain equal in size. So T2 is greater than T1. So you can say that Ni at T2 will be higher than Ni at T1. Okay. So this is what will happen for intrinsic semiconductor. Now intrinsic semiconductor has lower conductivity, and to make devices generally we dope the semiconductor with a dopant, and these doped semiconductors are called as extrinsic semiconductors. And these extrinsic semiconductors are of two types, one is of N type and second is of P type. N type is the one where you have doped with ions which donate, or doped with impurities which are also called as dopants, which donate extra electrons, and these are doped with impurities which donate extra holes. So these electrons will go in conduction band and these holes will go in valence band. So generally for something like silicon, if you have silicon has 4 of these electrons. Okay. And so you have multiple silicon atoms, and these silicon atoms are coordinated in such a manner so that each silicon is coordinated by 4 silicon atoms. So you have one silicon atom here, another silicon atom here, another silicon atom here, another silicon. This is a simplistic design, although the tetrahedral coordination is not like this. So this is silicon, this is silicon, this is silicon, this is silicon. So it has 4-fold coordination from each silicon, so that you have covalent bonding and you have sp3 hybridization. Now when you replace this silicon with phosphorus, let us say, so this is silicon, this is silicon, this is silicon, this is silicon, these have 4 extra so this electron, this electron, this electron, this electron, they all are shared, but phosphorus brings an extra electron because phosphorus is plus 5 impurity, silicon is plus 4. So this extra electron is the one which is because of phosphorus atom, and this extra electron goes to conduction band and it makes it a N type semiconductor. So this extra electron is goes to conduction band, leading to a N type behavior. So what it leads to in terms of band representation is, we have silicon whose valence band is here, we have conduction band here, this is EV, this is EC. When you dope it with phosphorus, phosphorus creates an energy level which is called as donor energy level, ED, and phosphorus, for each phosphorus atom, if you are able to ionize all of them, then these electrons cross to conduction band, provided this donor ionization energy, the difference between EV minus ED is small enough, of the order of Kt. So, which is generally the case, and phosphorus will ionize and give all its electrons, extra electrons away to conduction band. So, in this case the number of carriers basically Nd becomes almost equal to Ne. So, if you for example dope with 10 ppm phosphorus, 10 ppm will become 10 to the minus 6 parts per million, right. So, 1 part per million, which means 10 to the minus 6 for every part. So, basically if in a million you have 10 of phosphorus atoms. So, based on the concentration of phosphorus atoms you will have the carrier concentration. So, in a given lattice, if the number of atoms is 10 to the power of 24 per centimeter cube and intrinsic carrier concentration is about 10 to the power, let us say I do not know, 14 per centimeter cube at a given temperature, let us say at about 298 Kelvin. So, let me get the exact numbers. So, Ni is about 10 to the power 10 for silicon. For silicon it is about 10 to the power 10 per centimeter cube at 298 Kelvin. Okay. Now, this number can increase to, if you dope phosphorus with 10 to the minus 10 ppm, 10 ppm is 10 to the minus 5. Okay. If you have 10 to the power 24 atoms per centimeter cube, this becomes, so Nd will become 10 to the power 19 per centimeter cube. So, you can see that Nd is much higher than Ni, and if all the Nds are able to contribute to electrons, which means Nd is almost equal to Ne, and this is much more larger than Ni. So, for an N type semiconductor, N is equal to Nd. However, because of mass conservation, Ne into Nh is always equal to Ni square. When you increase when the electron concentration suddenly increases, then recombination also increases. So, when the recombination increases, then of course the whole concentration also tends to decrease in the valence band. So, as a result, this relation has to be always followed. So, for a N type semiconductor, this Nh is equal to Ni square divided by Ne, or it is equal to Ni square divided by Nd. Okay. So, for an N type semiconductor, in summary, you have Ne is large, almost equal to Nd, and Nh is small, as against a intrinsic semiconductor. If you take for a now p type semiconductor, p type semiconductors are doped with impurities such as boron, which are trivalent impurities. Okay. Phosphorus pentavalent, these are trivalent. So, when these are trivalents, then if you make the same configuration, you have these silicon atoms, silicon, and then you have boron. So, boron comes with only 3 electrons, silicon has 4 electrons to share. So, this boron atom now, it basically, you can say, now where does it need to bring an electron from? It cannot bring an electron, it is short of electrons, right. So, this creates a hole in the valence band. So, so this will be basically, you can say, 3 electrons are shared, and this is basically, you can say, there is a hole there. So, basically what happens is that in the band diagram perspective, this is conduction band, this is valence band, this is EC, this is EV. The p doping will causes energy, will create energy level EA, accepted energy level, which will take the electron from here to fulfill its configuration for the bonding and leaving a hole. So, it will take a electron from somewhere here, leaving a hole in the lattice somewhere. Okay. So, to make this covalent bonding, it will create a hole somewhere else. So, this is the hole that is created. It has taken an electron away from some silicon. Okay. So, essentially it will create holes because these electrons will go here to the, so this is acceptor energy level. So, this is again, this energy level is EA minus EV is of the order of KT, and that is how p type doping will work. For a p type doping in the analogous manner, this NH is equal to Na. As a result, Ni square is equal to Ne into NH. We can write this is equal to Na into Ne. So, Ne is equal to Ni square divided by Na. Another thing that happens in these semiconductors P and N type is the Fermi level tends to shift. So, change in Fermi level. So, the Fermi level for a intrinsic semiconductor is here, this is EFI. For a P and N type semiconductor, so this is EFN, and this will be EFP. The Fermi level tends to shift up for a N type towards the conduction band, this is EC, this is EV, and Fermi level tends to shift down for a P type semiconductor. Okay. Now, this has repercussion in terms of what we drew earlier, the energy band diagram. Now, you can do the similar energy band diagram picture that we did earlier. For we drew that. So, now if I draw this in this fashion, let us say this is EC, this is EV, and for an N type semiconductor this is EF somewhere on top, this is EC, this is EV. If you plot density of states DE will go in this fashion, on this side like this, on this side in this fashion. If you now plot the Fermi energy would be, the Fermi energy will go, so this is Fermi energy. Now, we want to plot the probability of occupation. Probability of occupation will go as, if this is 0, this is 1, this is half, it will be symmetric around this point. So, essentially you can say it will go in this fashion. Okay. So, this is 1, this is 0, this is Fe. So, the center point has shifted to top now. So, now if you want to plot the electron concentration, so electron concentration, I can use the same color for lines, these are the blue lines here, again the blue lines here. Now, if I want to plot the electron concentration, since there is more area here, this gives a bigger lobe and this gives a smaller lobe, much smaller lobe. So, this is Ne and this is NH, and you can see that Ne is much larger than NH, and this is because the Fermi function has shifted. So, it is not drawn very nicely, but it is sort of little, it's like this. Okay. For a P type, on the other hand, you can draw it in a different manner. For a P type, if this is EC, this is EV, the Fermi level is now here, EFP, this is EFN. Again, I want to make the same things. So, here I want to plot DE, I want to plot FE, and I want to plot NE or PE, right, NE or NHE, or basically carrier concentration. So, if I want to plot for this will remain same, the same behavior. In this case, now the Fermi level has come here. So, Fermi level has come here. Now, you can see that the Fermi level will, if this is, let us say 0, this is 0, this is half, this is 1. Okay. So, it will go something like this in this fashion. Okay. So, it will have more area. So, this is 1. So, it will have more area here, but it will have no area on the other side. If it is, in fact, I have not drawn it very well, but it would be something like this. Okay. So, there will be some area on this side. Let me see if I can draw it a little better. Okay, basically you can say this curve will go something like this, okay, and it will go something like this on the other side, touching 0 here, okay. And now if you plot electron and hole concentration, the hole concentration will be bigger and the electron concentration will be smaller. So this is NH and this is NE, and NH will be much larger than NE. So this is the difference between the P and N type semiconductors in terms of their concentration. Now, so this semiconductor, the last thing I would come to, what is NC and NV? So expression for NC and NV we will see in the next class, but we will just see how the semiconductor behavior changes as a function of. So what happens is that when, so this is your N type, this is your P type, this is EV, this is EC. For a N type semiconductor, if this is the intrinsic level, for a N type semiconductor this Fermi level is somewhere here, and for P type the Fermi level is somewhere here. This Fermi level keeps shifting to upside as you dope more and more. So with doping it increases up, so N type doping, right, and this will shift towards EV with more P type doping. And if you keep doping them, they will keep shifting up or down. So when the difference between EC and EFN is less than 3 kT, or when the difference between EFP and EV is less than 3 kT, then they tend to become what we call as degenerate semiconductors. They become degenerate semiconductors, or more like a metallic behavior. They become more and more conducting. So you will see in certain circumstances N type is heavily doped, P type is heavily doped, which means their Fermi levels are very close to conduction band or valence band. So this is what we have done today. We have looked at the carrier concentration and the reason behind having higher and lower concentrations and the expressions, and on this we will further dwell in the next class to look at little bit more analytical treatment of carrier concentration and Fermi energy in the next lecture. Okay, thank you.